Let me know if it is. Yes, it is visible or not.
Yeah.
Okay. Right. So again, good morning to everyone. Today, what in this session I am going to talk about the autoencoders, their utility, and different variants of the autoencoder. Basically, there are so many different autoencoders have been developed. Already in the last 2-3 days, you have gone in the detail of various this deep learning models. And this deep learning nowadays is a buzzword, and everyone everywhere is using in a different applications. So today I will talk about the autoencoder, a little bit about some mathematical aspects of the autoencoders, and then the current latest one, variational autoencoders, also I will discuss. And then I will connect. I will not discuss the GAN model, generative adversarial network, but then I will give you that from where people leads towards the generative adversarial networks. So these are the important aspects which you may feel, which who are more interested about knowing the algorithm inside how it is working. Apart from that, those who are interested only to use these algorithms, also they can use in a different applications wherever they feel suitable to apply. So let's beginning. I will talk about. I'm hopeful that you all are knowing about that PCA kind of algorithms or dimensionality reduction kind of algorithms. And what we do in the PCA, though PCA is not going to cover this, the principal component analysis. So what we do linearly, if we have 10 features in a data sets, so what we do out of 10, we extract some new 2 or 3 important features using this eigenvalue and eigenvector concepts, and then we use that new feature extracted features as important features, and then we build up our models like any classification or other clustering models on those new extracted features. Now in the autoencoders, you may think about some applications on that. It's basically the first utility claim way back for, you can think about if we have the unlabeled data most of the time, so how we can play. The labeled data sets are there. So in that case, already you have gone through that CNN and other algorithms or RNN. You can play with that and you can achieve your accuracy or target which you want. But what happened if you have the unlabeled data? Only the data, but you don't know the labels. But you want to extract some features. So how you can do that? So that's those some details I will discuss in this session. So we move ahead and let's just see this, what this autoencoder means, and I will try to explain. So whenever if anybody have any questions, so feel free to discuss in between, because at the last you may not be able to remember what I discussed. So at any point of time, if you have any questions, so just stop me and ask and discuss. So you just see this picture, what we want first. We have the image. So, and what we want to reproduce the same image of this cat. We don't, means I have the image, but I'm not telling that it's a cat image or something. We have the image. For example, we have in every one mobile have so many images, and all are unlabeled. Unlabeled means you don't have put any tag on that he or she is your friend, your wife or spouse or daughter or something, or this is a cat or this is a dog. You have not put it any kind of tag on your data sets which are available on your mobile phone. I'm talking about especially the image. So it's a unlabeled data which you can use it. But the question is, can we get some features, important parameters, which are important to reconstruct the image of like if I will concentrate more on the animals, and I have this cat and dog or some other kind of animals also. So can we get some important features of those images so that we can reconstruct again the same image? Or what is the idea is that we have an image. I want to represent in such a way in some other domain or some other space such that from that space I can again regenerate the image. Let I connect my this part. If you understand, then I'm sure that other detail philosophy you or methods easily you can understand. Look at this part. I will try to just give me 1 minute. Take my pen. Okay. So what is the idea that we have some image here. We want to move or represent because numeric value. Imagine you know that this is the matrix form, some numeric value for each image is there. So this is the input. We want to represent some, so it's a matrix. So each image in the matrix form you have. The idea basically is that and then from this, so this is, you can say a x which is represented here. From this we want to get this representation or hidden layer or new vector, and from this again we want to generate the same x. This task, something is creating problem. My board is creating 1 minute. So this task of doing or learning representation is important one, and how we can achieve that. Basically this part, original input, is like a neural network. So this part you can say is one neural network, and from this again we want to generate a new xcat. Then you can ask that why we want to do that. Why x to hidden and hidden to again x? Why? What is the benefit of that doing? What are the important? If I have an image, from image I want to get a x hidden units, and from hidden units again I want to generate xcat. So what are the important of that? Why we are doing and what we can achieve? That I will show you some examples. So this part of from input to moving on the hidden units, or you can say representation stage, is known as encoding. And from encoding, whatever the hidden states you have made, from this again reconstructing this image is known as decoding. So the two part of this in the autoencoder is encoding and decoding. So what it means, we have X, we will pass through a network. Network means ANN I'm talking about. We pass through ANN or network, and then we get this hidden units. This part is the representation is known as encoding. In means representing a meaningful things, meaningful way somewhere. We don't know what is that. We will train and then we will get that value. And then decoding means whatever the encoded things you have achieved, from that getting again or reconstructing again this the image which you have used as an input, is that's what known as decoding. Important parameters in autoencoder: encoding and decoding. Whatever you have represent somewhere in the matrix form or vector form, and from there again decode that. So this part of mechanism is auto encoder. self-encoding, no label. You are not telling that this is the image of cat. You are saying that we have an image. I want to learn some hidden states or some representation so that I can reconstruct these image again from the data sets. Okay. So two possibly a non-linear function is basically important in every autoencoder, and that is encoding function and decoding function. This HFX denotes encoding for the input X. So again, I'm trying to explain that this is encoding and getting this G. For G function, this input is now the hidden units. We are getting X cap. So G of Fx, you can say. From X, using this F encoding, we are getting a representation. And whatever the representation we are getting from that, we are again applying this decoding function and we are getting the new image. So this is reconstruction or the decoding for the input X. For an autoencoder, F and G are learned with a goal to minimize the difference between X cap and X. This is the autoencoder. We don't know what is suitable F and what is G.
Not audible, sir.
Yeah, not audible.
Representation for the input of X. Means what is we are doing that from the input, we are getting some kind of other nodes, and from those nodes, we are able to generate again the same kind of images in this case, which we have used for the training purpose. So just the see the thing is there. To getting that is hidden units, you are using the actual image. But this reconstructed image, you are not using directly, you are not passing this directly. From this hidden weight value, it means some weight numeric value, you are able to generate the image. This is the autoencoder part. So this is also known as autoencoder is also known as feature learning. What we are doing, some feature we are learning. And those features are able to give us this again the same image. So feature learning, that's what I said, that feature extraction PCA, you can think about as a simpler form of this autoencoder also. A special case of this, you can say, but autoencoder is many more things, not only the PCA.
Sir, we can have inputs as images only, sir.
This autoencoder, there are for text also, there encoding decoding patterns are there also. In the text NLP also you can use.
Okay, thank you, sir.
I'm using this, that playing with text images are much easier to understand compared to text. Okay, so you can use it. So I hope now you are getting what is autoencoder, input and output. But in between, directly we are not copying this input to output. That could be happened. Then if it will be there, then you are not learning anything. No property you are learning in that case. That could be a problem, which I will discuss how it can be handled. Therefore, autoencoders can also be used for feature learning. One important point, just keep it here. What is happening that from the image, you are getting the hidden weights. Assume that it is valid and true. And from this hidden weights, you are getting the output. This input is not going to be used here. Okay, this is in combination is going to be used. So this hidden layer is affecting or combining in such a way, it is leading towards the same image what the image you are giving here. So this value, this is very, very important. And later on, I will show you that variational autoencoder and that how the people have thought out about the generative adversarial network. That idea, little bit, I will talk about that idea today. So this is also known as feature learning. And the size of the hidden units can also be larger than the input. This number of hidden units, it may be less than the input. Then it will act as a PCA kind of things, dimensionality reduction kind of thing. It could be larger than the input also, that can be in sparse kind of representation in many larger domain. It's also needed sometimes. So many way you can vary this hidden weights. It's not necessary to small, or it not should be always greater than, depending on the application. If you want to do the compression or something, then you of course go with the lesser number of hidden units. Okay, so little bit I will talk about the maths, not too much detail, don't worry, it's so simple, but I will try to explain what is happening inside this autoencoder or plain autoencoder. So let's assume that a single hidden layer, just assume that only one. It could be a multiple hidden layer like seen in another, but here you just try to understand only one hidden layer. You can put encoder as a CNN and decoder as a CNN also. Multiple hidden layer also in the encoding part and decoding part you can put. But right now you just think the simplest model, what we do with NN or multi-layer perceptron, we play with one hidden layer. Same way you just think about only one hidden layer in autoencoder. In this case, but input and outputs are, it's not the level in the output, only the what is the input, we are trying to reconstruct the same its output. So let's assume that only one hidden layer with k plus 1 means k number of nodes hidden, and it hidden value may be any k dimensional vector. Now we can define what is the linear autoencoder H, what is H, and what H means this part. What is H? If you recall the multi-layer perceptron, what is H? H is a combination of this, you can say x1, and this weight, if you say w1, x1 w1 plus x1 w2 plus x3, so those two, then x2 w1, x2 w2, like that. H multi-layer perceptron is what? It's a linear combination of weight plus sigmoid comes out in multi-layer perceptron. So what is happening in that, basically wx plus b means, here you can understand, just for sake of understanding, I am just writing. Okay. So w, if you say this part, and this is creating problem. Okay, I will take my, just 1 minute here with me. So wx is not working properly here. Wx means, you can say this is a vector form. So you can say this weight is w1, this weight is w2, this one is w3, this one is w4, w5, w6, w7, w8. So for all you just give one weight, and you can say x1, x2, x3, x4, x5 for this case. So wx means all this form means all the combination means W1 x1. If this one is W2, so W2 x1, W3 x2, W4 x2. So all combination, you just product of this weight with this input, product of this weight, this input, and take the summation. That's what the meaning of Wx. Product of two vector, nothing else. So that way you can understand. And one term bias has been added. I hope it is clear to everyone. This is what the meaning of this Wx plus b. Okay. Wx plus b means W1 x1 plus. So this is the input part. I'm talking about this part. Same way, this is known as H. H is fx. So fx is Wx plus b. Same way, x cap means the output in this case is you use W star H. So this weight now again here you assign, and W star you can say this weight you can say W. This one you can say W star, and this one is going to be applied with the H to get the output. So x cap is W star H plus C, another bias term added here, another bias. This is simple, like you just think about multilayer kind of perceptron. Without sigmoid, or later on you can use here sigmoid also, no problem. That's what we do in the ANN and multilayer perceptron. Well, so once you define this, what do you have to do? Let's see that. So basically, this encoding function f, decoding is giving output. Input and output have the same dimension here in this case, you just see. But hidden unit can vary the dimension. It could be a lesser than the input, or it could be a larger than the. So this one bias term has been added for hidden unit, means for this. Another bias has been added for this output also. And W is a weight here from moving from this to input to the hidden, and W star is a weight from moving from hidden to output layer. We have considered only one hidden unit. You may think about multiple hidden unit also, that could be. Now, this is the whole problem. Then what I have to do? How I know that? How the weight value will be learned? What will be the error function in that case? That's the new thing comes up. Once the structure I have made, what is our target? Our aim is to learn the weight values of W is unknown, not known. Hidden nodes values are not known. So what we want? We want the weight value such that X becomes X cap, or X cap is closer to X. That is our ultimate target. In between, once we are able to do, the error comes out closer to 0 or as minimum as possible, then we can say these hidden states are good representation, or this feature are very, very important features and able to generate our output. How we can do that? So to learn this weight, or to learn F and G, to minimize this S cap minus X square, this is a norm. So basically most of the time, this is the distance, Euclidean distance we can use. And some cases what happen, if we are using the linear one, we instead of non-linear autoencoder. So non-linear autoencoder, so we are not using any sigmoid here. Once the moment you put sigmoid function in that, it becomes a non-linear. Okay, so there are many ways. Sometimes people assume that W star is equal to W transpose, means whatever the weight value is here going to be in the reverse way the output. It could be, you can, this is the assumption. This is not always going to be, but in many ways people play with that. And it's equivalent to when it will be principal component analysis, you can say the same thing will be a principal component analysis. Don't use the sigmoid, one thing. And second, this W star you put at the W transpose. I hope you all are knowing some maths. So W is the weight matrix. You just take row, column, row, it becomes a transpose. And same way you just put it here, means the weight from 2, 1 is going to be weight for 1, 2. That's what. And it will act as a principal component analysis. The same autoencoder you can play with the principal encoder. So this is the linear. You all know that this PCA is a linear kind of feature extraction, but not necessarily only the linear part of feature extraction is present. sometimes we need a non-linear feature extraction techniques, which can be used, which I will discuss. So let's see this. What I said that the W star equal to W. So just see the more detail inside, how it look like. So not all is shown. So this means to just, this could be connected to everyone. This one is could be connected. So this is just for discussion. So WH connection for this to this, and then one is connecting to this 5. Then 5, if you represent all this in the matrix form, for W star, what we are saying that in the case of PCA, just take the transpose of this and you can get the autoencoder as a PCA part. If not, then a different kind of structure you will get, which I will discuss. So W is a matrix weights of edge between input and hidden layer. So this one, this matrix, this whole thing you can write, if this is K, you can write as a K cross D matrix, W as a K cross D matrix, and then this is the W. All weights you can write in the matrix form. So already, so W star DK is the just reverse that between hidden layers to output layer. So first W is from input to hidden, and W star is from hidden to output. So in that case, this representation is this way. And some cases, this autoencoder is used said to have a tied weights, means if this condition we are assuming, not necessarily already I'm telling that some cases we assume that it's a tied one, means whatever this one is, that take the transpose from hidden to output. Well, so that one, what I said that the linear autoencoder. So we have not used the sigmoid for the hidden units. Whatever the W comes out, weights comes out H equal to WX plus B. Directly we are using, and it will act as a PCA. In the nonlinear case, what I said that the same thing. You just recall what is happening in multi-perceptron algorithms and what happened in the perceptron to multi-perceptron and nonlinear this. ANN, what happened that you can play with without sigmoid, then you see what will happen. And if you see this sigmoid or any activation functions, then what happened? The power of ANN increase. It means it can approximate any kind of function theoretically. So this non-linearity, sigmoid or ReLU, whatever you are going to use, that advantage is that, okay, PCA learns the linear features. So data sets are in the linear directions only, but not necessarily. Sometimes data sets are distributed in non-linear distribution fashion. So in that case, this non-linear autoencoders are going to be very, very helpful to learn the distribution of the data sets in a manifold or some other nonlinear cases. Just so till now nothing new. Already what you know in ML are basically multi-layer perceptron, which has been discussed in detail. Same thing we are using here. In the previous for the PCA, you said that I said that WX plus B you use. Now I'm saying use sigmoid. And what is sigmoid? This is the sigmoid function. So everything what will convert, whatever the WX plus B comes out, sigmoid converts between 0 and 1. Okay, so kind of you can think about the normalization, kind of between 0 to 1 you are mapping and then we are getting something. So you use this nonlinear activation function as an input part as well as the output part. Most commonly used autoencoder use such a nonlinear transform, because for the PCA part is one is what I said that PCA as a special case for autoencoder. And you can use as a PCA also what I discussed that without activation function. With whatever the input side, hidden nodes have a less number of nodes, and then you play. But in many applications, you need this non-linearity. And for that, just sigmoid or ReLU or any activation function you have to put after this WX plus B, so that you can scale down non-linearly this thing, all the value of WX plus B between 0 and 1. What learns by autoencoder, you can see that. We learned the weights. And these weights are, and if this hidden this W and W star, what is happening that this some small or some important features we learn through this, because H is Wx plus P. So we learn this W basically in this case. We learn this W, which is the weights, and basically they have some kind of weights are reflecting, you can say, some kind of features of input data sets. Possible patterns or feature of the training data. Or you can say K basis vector in PCA, but just don't. So it captures some important features. We don't know basically what are the important. Just the network is learning from the data sets during the training, and it is giving important parameters. For any input X, the encoding H tells us how much each of these K features is present in K. Okay. So how to train this autoencoder? What we have to find out, the loss function we have to X cap and X. The loss function of parameters, basically what we have to learn W, W star, B and C. And already I told that in general we use the Euclidean distance, squared loss, input a real value in that case for a single input X and its corresponding reconstruction output X cap. What we do, we measure the distance using the Euclidean distance formula. That's what the L2 norm is. And then what we do, as we in the NN or in other applications, you just try to minimize, apply the back propagation, get there as close towards zero as much as possible. And then you can say, okay, these are the weights, these are the hidden values, weights for this encoding part, and it is ready as an encoder decoder model, the autoencoder. Another scenario where inputs are binary, you all are aware about that the cross entropy loss and the kind of loss which could be also used in this case. So the whole idea is we find the weight unknowns W, W star, B and C by minimizing the reconstruction error. This is the reconstruction error, either this loss, square loss or cross entropy, depending on the problem where you are using this. This can be done, what I said, using back propagation already. So what happened? Two, three different scenario occur once you play with this. Already I am now hopeful that any query from anybody, then I will take, then I will come to this under complete, over complete, and need of regularization part. Anyone have any question? Okay. So no one have. So that just see the two scenario and what will happen. I said that number of nodes, hidden nodes, may be less than the input node. The first case you see. K less than D. Another case, it could be greater than. So it may be, sometimes it could be under complete if the number of nodes are less, and if number of nodes are greater than, it can be over complete. What it means that and why this is the problem. These are the hyperparameters becoming, and the tuning of the hyperparameters are one of the challenging part in every deep learning machine learning models. How to set the parameters, how many hidden nodes, how many nodes, if dropout, what should be the value, if regression, so what should be the value. So all these are very, very important, and some the people design these things for the specific task. So in both cases, it is important to control the capacity of encoder and decoder. What it means of the capacity. If you know the underfit and overfit scenario, the capacity, what happens, it should not be Like that, if you are making a model, what is happening in machine and deep learning, and what we do? We have a data sets and we made a model. Then job is done? No, the job is not done. The model will be good if new data set comes out, and the performance of the model also will be better in that case. Otherwise, this model may not be good. It is too much trained, accuracy is perfect, but during the testing purpose, something new challenging comes out. If some performance is poor, so in the machine learning and deep learning, we don't prefer such models. The idea is generalization in ML and DL. Means whatever you are doing during the training purpose, okay, fine, you are excellent and someone is very good, model is very good in the during the training, but the performance during the testing where the new data set, unseen data comes out, the model performance would be better in that case. So the whole idea is how we can do that, how we can get it. It should not be overfit or underfit scenario, and how the in between the balance we can make. That's the important point is. And the capacity control means what is here, I would like to highlight. The model you have developed and such a strong capacity that it memorizes each and everything. Like the spoon feeding, everything you know, you just see me and I will remember. But anything new comes out, I don't know. So too much control the capacity, increase the capacity, it may not be well performed in the new data sets. And too less poor capacity also it will not. For example, I used to take this example, the classroom teaching. Not necessary that those who are the real world problem solver, those who are solving most of the challenging tasks and innovation or doing innovative work in the different domain of the research or any other work, not necessary. Maybe someone are good. Not necessary that each one of them is this that year topper of the batch. Not necessarily I'm putting that. The same way that because the new challenges comes out, who is able to take that challenge, able to solve and innovate, that is more important. Not necessarily what is the topper or someone is there in the classroom or in school or something, some engineering, is always going to solve the best. Not necessary. So the same thing in the machine learning. Though during the training, the model which is perfect, not necessary that he will perform after the training during the testing. So this control of the capacity, how we can control so that it could not be overfit or spoon feeding, or it could not be, you can say, not trained at all, not knowing anything. So that is very, very important to control. Otherwise, it becomes very, very difficult. So under complete, imagine k equal to 1, means 1 hidden units and k number of nodes. Very powerful F and G can achieve very small reconstruction error, but the learned code will not capture any interesting properties of the data. In case of, we are talking about in case, sometimes it may, sometimes you're not sure that can achieve even geo reconstruction error, but the learned code will not capture any interesting properties of the data. So, well, this is very fuzzy things. I'm talking about interesting properties of the data. What do you mean by interesting property? When you can say it's interesting or not. So all these terms, if we are using that, the idea is, okay, the model is trained, accuracy is there, but if any new data comes out, how it is going to perform. And if something is underfitting and overfitting happening, some cases it is going to fail, then people have designed, such as have designed some new kind of algorithm, okay, play with that so that it could be more generalized and more better autoencoder. It is therefore important to regularize the function as well as the learned code and not just focus on minimizing the reconstruction error. To avoid any kind of skewness in the learning process, this regularization in the autoencoder is also very, very important, as it is in the all deep learning models. Because any deep learning model without regularization, without that, it may be flawed and one-time success. So we need to regularize, control the capacity to achieve the accuracy. So regularizing the autoencoder is a very, very important phenomena, and two different kind of algorithms based on this. One is sparse autoencoder, and another is denoising. I will talk about that. What is sparse? Yes, yes, please.
Sir, may I ask one question, sir?
Yes, please.
Sir, like when we know the problem statement, it is classification. So in the image, so what we did was we tried to convolve it with filters. So the filters we have designed in the layers. Okay. So now when we come to this problem, how the system understands that this is a replication problem. So then you told there will be autoencoder functions. So that means whatever are state of art autoencoder functions, that has to be imbibed in the network. I am just thinking how the network knows that this is actually a replication problem. Like
Oh, no, that's okay. What happened in the CNN? What do you do by the CNN?
in that we have this conf 2D, conf 1D, where we will have this tiny metrics.
This is
So
inside one side.
by
Okay,
the
okay.
weights are randomly done, and then it
Okay.
tries to learn. So I was
What they
thinking
try to
here,
learn?
learn. It is trying to see some pattern basically. So say for example, the tiny matrix is taking one 45-degree angle line. So it is trying to move it over
Okay,
the
give me
image,
one
and then
example. Give me one example where you can think about to apply CNN so that I can explain more detail. Where
uh,
you thought that okay, in this problem I can apply CNN.
okay. So we have been shown that we have done the classification,
Sure,
whether
sure, sure.
face recognition or animal or dog, whatever
Good,
is
good.
that.
Yes. So
So
what happened? What happened in the classification problem? If you give the image input, then you know that the label means you know that the Y value it's a cat or dog. Am I right?
yes, yes,
So
yes,
this is supervised learning problem. Okay.
correct.
What I'm saying that I'm giving the image, but I'm not telling that it's image of cat or dog.
Yes. So what will be the output column? Here the output column was 0, 1, 1, 0 or something
Here
like
the
that.
output column is same as the input matrix.
So same to same, we will be giving the whole. Say if it is 28 by 28,
No,
then the
no,
output
no, no, no.
will be
Output level. We are not giving this output x cap. If you see here, x cap is there.
yes,
This x is the input. Okay, actual one.
yes,
From
yes.
this we are getting this hidden weights, and from this head we are trying to get this x cap. Directly we are not passing this. Okay.
Okay,
So whatever this reconstructed x cap is there, it should be
okay,
closer to the x. Our aim is it should be closer to x, but we
okay,
don't know. You are generating through this. It may comes out a vector which is far away from this x. Okay.
okay,
The whole
okay,
idea is this x cap we bring towards closer to x, and what happened during this optimization process, this new weights value will be learned. Am I right?
okay. I think once I see the code, maybe I will get the clarity. So presently, we don't have X cap, basically X only, and then we will be adding layers, and finally the output will be generated. Something
We
maybe.
don't have the x cap. X cap you are generating from this decoder function. Okay.
Okay.
And this x cap once will be generated, then how we measure that this x cap is good or bad? For
That is
that,
loss
what
function. From the loss function will
loss
come.
function. That's what the game. This is the what the encoder, auto
Okay,
encoder. So
okay,
once we get suppose zero error, then the
okay,
idea is this x cap. If suppose it becomes closer to X, then some weights we have learned. That's what we learned in the CNN. We learned some weight. Am I right?
Yes, yes, yes. Through
Same way here
epochs.
we learn some weights.
Through
Okay.
epochs we have learned, but here also
Yes.
we will be doing calling the same thing many times till we minimize the error.
But the only thing is that here levels are unknown. It's unsupervised.
No, it is, yes, yes, yes. But the x cap minus x will be minimized, has to be
Yes,
minimized.
X cap minus X should be minimum.
Okay, okay,
So
okay.
this is
Thank you.
the main application is that most of the data sets which you have are unlabeled. Labeling a data is a challenging task.
Yes, correct. It's
You all
unsupervised.
have already, I said that we all have on the mobile phone that so many images, and most of them are almost all are unlabeled. You personally know that this one, he or she is my relatives, and this is the image of cat, this is the image of dog. Am I right?
Yes, sir. Yes, sir.
So what happened
Sir.
to kid? Kid is not knowing this is tree or cat or dog. We tell them.
Yes.
So this is a different class of the problem where I am talking about labels are unknown.
So in the supervised, when the last layer comes where we do the softmax like understanding, before that, if we take that layer, then we can have the feature learning, correct? So there we can segregate the classification part, and before that layer it will be feature learned. Am I correct, sir? Correct.
Yes.
So like
Somehow
that, this is another way of doing feature learning where we are doing. I'm just thinking.
this is also a feature learning. Yes, you may think about that. It's
Yeah,
also
I
a
was
feature
just
learning,
thinking.
but in
Yeah.
this case, labels
Okay.
are not known.
Known and one input only. Maybe one cat only I am able to encode. Correct. Here I am not giving 200 cats to encode. Correct.
You are giving the input, but not telling that this is a cat.
No, no, that is okay. Say if I am giving one cat and it is trying to learn a feature which how the cat looks like, the important
Yeah,
features. So
you
this
can say
time
that.
am I giving 200 cats or I am giving only one cat?
No, no, we are giving 100 to 200 cats also here also.
Okay. Okay.
The
Okay.
only
Okay.
thing is that in the supervised learning, you are telling that this is a feature of cat, this is a feature
Yes.
of dog.
Yes.
In
Yes.
this
Correct.
case, you
Correct.
are not saying that this feature is a cat, this feature is a dog.
Okay. Okay.
This
So
model automatically had to learn that what is this feature, important
okay.
feature for. Okay.
Okay. So in both the ways, I am able to do feature learning. My point is that one is
You can.
unsupervised manner, another is supervised manner.
Yes, yes, you can. But both have a
Oh,
different kind of applications and
yes,
different.
yes, yes,
Even
yes.
CNN you can use here as an encoder function and decoder function also. That I'm not going.
Okay,
Otherwise, you will
okay,
be
okay.
confused. Right now, I'm taking one. So
Yes, yes,
you, as a layman, you can understand that here labels are unknown. We have some
yes.
image. Like suppose, do we have a representation or a matrix? Suppose a matrix representation such that from that matrix, all the images which are available on your mobile phone, I can generate. Can we get a representation so that all the images which are available on my mobile phone, I can generate? Is it possible?
Okay,
Can we do that?
okay,
If it
okay,
is suppose, this is the representation kind of learning. For
okay.
example,
Understood.
suppose I
Understood.
have
काम
a,
नहीं कर रहा
suppose I am a
क्या था
person. Hello.
Yes, yes, yes. Understood. So this is a representation type of learning that's
Yes, it
understood.
is a representation learning. We are representing in such a way that from that representation we are able to again reproduce the same image or multiple kind of variety of image.
Okay, okay. And the representation is compact so that we are
Compact.
trying to do a dimension reduction in features as well as.
It can be used as a dimensional reduction. It can be used in some other applications also.
Okay, because either the very easy way is identity matrix. That way, to anyway can generate. But here we
That
are
is the
trying.
problem. That is the one of the problem in this autoencoder, and that's why this I'm talking about this sparse denoising, so that
Okay,
we can
okay.
avoid. If you put the identity matrix here, then you are not learning any feature.
No, no, no. We are generating that m into n times that only. The
So
same.
that is the problem. That is the challenge, and that's why people have designed this sparse, denoising, and various algorithms. Okay.
Okay. Thank you so
Okay.
much, sir. Thank you.
Okay. Thank you. So, just a minute. I will take water. Then I. Okay. So what I was saying that. So, Madam had pointed very well that identity matrix. This is the problem. This what I said that complete, incomplete, and some issue is there, and that's why we are looking for regularization. Otherwise, what happened that if you put here identity matrix and multiply, you will get the output. A matrix multiply with identity will give you the same matrix. But this identity matrix has no use. Nothing you have learned. Not an important features you have not learned. What I said in the previous slide. We want to learn the important features so that we can reproduce. We don't want to namesake that identity matrix, no features, and again reproduce. Then we have not learned anything about that data sets. So for that, is people have used this sparse autoencoder is one way to regularize. Another one is denoising. So in the next slide, I will discuss this denoising autoencoder. These two are very famous one. Apart from that, there are so many. So one or two more I will discuss. So just see what will happen. This in a sparse, you know the sparse. I'm hopeful that you all are knowing that L1 regularization integration. We use L1. L1 means mod function used for regularization, and basically it acts as a sparse. Sparse means what it does. Most of the weights value it will put at a 0. This is the sparse autoencoder. A sparse kind of regulation whenever we talk about. So either L1 for that we used L1. L1 means this representation mod of this is known as L1 norm. So we use this L1 in regular this simple plane regression or in anywhere you can use this L1 also. So sparse it has very well studied form that what happened that if we use for encoder and this part has very few non-zeros. So most of the things weight value we put at the 0. So this is the sparse kind of autoencoder. You take multiple larger hidden nodes here and then use the sparse and then you can see, okay, we are learning the features, many combinations of the features, and it is able to generate this. So basically, it's kind of thing is like those who are knowing the linear algebra in a matrix or matrix theory, learning basis. What happens in the basis? In a three-dimensional graph or plane, two-dimensional plane, suppose you know the basis two vectors which are independent, then any points on the space that two-dimensional you can generate. The idea is borrowed from there, but I'm not going into too much detail. So here also the sparse means we will learn so many hidden nodes, but so many combinations we will put as a 0, which can lead us to get the x cap, which is closer to input. So the simple loss function has been added. This is the actual loss. This regularization function has been added and it becomes a sparse autoencoder. So earlier people have done this. By minimizing the above regularized loss function, you can play with that, apply your any back propagation as you did in the other back multi-perceptron to CNN and you can see the effect. Denoising autoencoder have a multiple application in image processing. Those who are working, you can see that denoising imaging, some image points are missing and that's are corrupted and I want to get the better one. So in that case, it is very useful. In some coming slide, it is there. What is happening in that? What denoising say? Okay, we have the actual image. What we do? We put a noise and we corrupt it, either missing or Gaussian noise. You just change some pixel value or something you can say. We have an input, some randomly cross point you can say you have changed. Now what you do, from this x cap, now you try to generate x tilt, you try to generate x cap. And then you try to this x cap should be equal to this. So instead of from original image to constructing this image, the idea is to develop this method from the corrupted input. Corrupt it using the noise, or it could be the case where something is missing. You have an image, some part is missing. It could be a corrupted one. So from that, you generate this actual one, generate something, and then in this particular case, since the original image is with you, so in that case, we have corrupted intentionally at some points. From this corrected points, you can again, what is the autoencoder you apply, but the error function is not this x tilt and x cap. Error function is x cap and x original one. So started with corrupted one, you are generating this x cap output, which would be closer to original one. That is the idea of denoising autoencoder. This is simple, just change and a lot of mathematics comes out, but this is the idea of denoising autoencoders. Is it clear to everyone? This denoising, just put a noise, move to x tilt, again apply the autoencoder, but the error function is x cap and original one, not this corrupted one. So from corrupted, you are getting this hidden unit and function, and then you are getting output. But the error you are measuring x cap and original one. So from corrupt data, you are trying to produce the original. So in between, what will happen? Once we learn such kind of models, it will be helpful to apply in image imprinting or some other missing image part. However, we still want to reconstruct x cap to be close to the original. Yes, anyone?
Sir, we have image processing techniques to add noise, Gaussian, pepper, salt, and all those things. So
Yes.
can we uh, put those functions here, or you are saying this is a different
Yeah,
way of
same function, Gaussian,
doing?
same. You have an
Okay,
image and you have to add some noise there. Okay.
okay.
So
So we can
you
use
have
the traditional IP processing here for
basically most of the time we use Gaussian noise, but you use any kind and
okay,
see that what
okay,
is the
okay.
impact.
And that array of will be, we will first do it pre-processing, and then we will put those vector of images in the layer, correct?
Yeah, both are there. This original one is now going to be used for the error function. Okay.
Yes, yes, yeah. Original
But
is
this,
one vector is 1 to m into n, correct? This is if
yes,
I say
yes,
one dimension. Now I
yes,
do
yes.
image processing separately. Now I get 1 to m into n of corrupted. That I will put it another
Not
layer.
too much
That's what.
image processing, or in the same layer, you can say one randomly put some noise, Gaussian noise. That's all.
Okay, 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 okay.
So we are
Thank you.
not going too much that any noise you can add. Most of the time we
Okay,
play with the Gaussian.
okay. Thank you, sir.
So you can vary and see that. So this is the whole idea is from the corrupt one, you are trying to get the image which should be closer to the actual one. Am I right? This is the intuition behind denoising autoencoder, removing the noise. So from the noisy image, getting the actual image, that's what the idea. How we can do that. In between, we are learning the weights. Am I right? And it had very huge application. You just Google it and see that denoising autoencoder is a practical application. Only thing is that since the corruption is stochastic, we minimize the expected loss in this case. Okay. The same thing I have taken somewhere some slides and to describe that, but I'm hopeful that it is clear. So I have to discuss some more things. So anyone have a question on denoising, then I will take. Otherwise, I hope now it is clear. Philosophically, it is just adding the noise, learning from the noise, getting the reconstruct the image, and just see that you reconstructed, it's closer to the actual one or not. If not, again do the back propagation. So once we do the noise at the starting point, so weight value just going to be back propagated. That's all. This is all about this denoising autoencoder. So loss function is already I told that. Okay, the same denoising means what is happening that actual image is like this. We have added some noise and become its x tilt. And from x tilt, we try to learn this x. This is just for understanding point of view. This is in between, in the bargain of that, we learn the weights which can handle the noise, some little noise also. This is all about this denoising autoencoder. Okay, this part, looking at the time, I don't want to go. Okay, so there are other kind of that. I said that it could be a one hidden layer, but now there are deep stacked autoencoder also. Some application in tomorrow's session in transfer learning I will discuss. So instead of like CNN and like multi-layer perceptron, you can add as much as hidden layer. Just see that. This part is your encoding. So from 5, hidden layer 3, and again hidden layer with 2 nodes. Then from 2, we are putting 3 hidden layer, just symmetric. Weights may be different. And 3, 2, again 5, because input dimension should be equal to output dimension. So in between, this is the decoder part. Architecture is same, or you can say encoding and decoder is the reverse image. From here, we are encoding and getting some hidden units. And from this, again, we are trying to reconstruct our original image. So multiple kind of variations you can do and see that, okay, deep stack autoencoder and how it is working. And then this is deep stack. So you go with the deep learning models, you put it either here CNN or many things, but up to some this, again, you have to apply for decoding part. So encoder, decoder, either deep models or the stacked autoencoder, also in the literature, current state of the art, you can see in a different, many applications. The whole idea is what you said, that learning the feature CNN also we are doing. Yes, CNN there you are using for that, but CNN in this way also you can use for encoding and decoding purpose, where data sets are unlabeled to get some important features to reconstruct. Another kind of, next half an hour I will discuss about stochastic. Okay, maybe I don't know, the little bit probabilistic comes out, but this is the current state of the art, or you can say that, okay, both have a different kind of applications. And this is a kind of generative kind of model. It's not a discriminative model. The previous one is kind of discriminative models, like CNN and all are discriminative, but this is a generative kind of autoencoder. And just before the GAN, I think 2014, and it was developed in 2013. This you will see that how it has been designed. But let's see, quickly I will discuss. In the probabilistic term, how we can represent the see it. Encoder means from given X to get hidden. This is the conditional probability. X is given, what should be hidden. And decoder is once hidden is know what should be the X or X cap, whatever the name you want to give. This is what the encoder decoder part is. So choosing the distribution depends on the type of data being modeled and the encoding. So this is basically the probabilistic autoencoder, how we can think about and how we can design. Here the, okay, this part I will discuss as I will discuss. Such idea has been designed to generative models, and let quickly I will describe what has happened the discriminative model and generative model. Like support vector machine, multi-layer perceptron, which you are knowing, all are discriminative kind of function. As a classifier, if you are using, so what we do, we try to get in the output layer, we try to put some boundary, and so that from the given X, we are trying to put the boundaries in the label so that I can say above this cat, below this dog, or like other kind of thing. So it's kind of mapping from given X, we plot the boundary on the domain of Y. What generative models say that, okay, this is the one kind of thing. if there is an image of cat, if there is an image of dog, can I learn the distribution of that image of cat, distribution of image of dog? Instead of only learning the boundary, can I learn this distribution of the data sets so that I can say that the distribution of cat, variety of cat images should be this domain. This is the distribution. And for dog, this is. And people have designed this like Bayesian model. It's one kind of this generative model. And generative adversarial network is another kind of generative model. So from learning the distribution and from the distribution, getting the, again, the classification task, if you're talking about, and that's what is the important part in the generative model. And in this scenario, generative models, we'll talk about popular example is variational autoencoder. So I will talk about that. Generate new data using a random code H. So let's, in next half an hour, I will discuss this part. And you all what, okay, I will go, I think that slide is, okay, before one picture I put it lost, sorry for that. I'll come back again and I will describe. You all don't, whatever the mathematics parts comes out, don't worry for that. Let's try to understand the concepts later on as per your need and as per your utility you may go. Okay, this slide is here, but I will explain the basic nitty-gritty, then leave it. The part of mathematics you are not able to capture. You just see this part. I said that it's a generative model. So what happened? In the autoencoder plane, I discussed that we have an image, we do the encoding, we do the decoding, and decoding, we get the image. What variational part says, do the encoding, learn the distribution. For example, let's assume that I'm encoding in such a way, you all are knowing this normal distribution. For normal distribution, we need mu and sigma, standard deviation and variance. So this is the normal distribution. This is the mu mean, and this is the variation you can see. This is what the normal distribution is. What is the idea is that from the data, we encode in such a way so that we can know the mean of the image and variance of the image. Once I know the mean and variance, it means I know this normal distribution. For example, you can say. After that, I will collect a sample from this. And this, from that sample, we generate, using decoder, we try to generate the image. This is variational autoencoder. What we do, from the image, encode, and then we learn the, you can say, the parameters of the random variable. Assume that it's a Gaussian. So parameters of Gaussian is mu and sigma. We learn this mu and sigma during the encoding. Once I learn the mu and sigma for encoding, from this I will collect a sample of data which follow this, means any data from this distribution, either this one or this one, and that data will be passed to the decoder, and this decoder is architecture which learn, and it can reproduce this image. This is what the variational autoencoder means. It's a generative. So we learn this distribution of the encoder part, means data part, and from this distribution, we try to learn the output. Again, try to produce the output using the decoding pattern. This is known as variational autoencoder process. Very, very useful. Once you understand this, the GAN is, okay, somehow you cut this part and this and merge with this adversarial part, it will become again. I'm not going with that. This is what idea of this autoencoder to variational and auto. In autoencoder is a non-probabilistic, we encoding and decoding. In variational autoencoder is a probabilistic and it's a generative model. Encoding, and we do the learn distribution mean and sigma, and from this mean mu and sigma we try to produce again the using the same kind of decoding function we try to learn the images, and again the same error function and all which I discussed we are applying. So let's more detail quickly in next 15 minutes I will talk about. I hope you are able to differentiate between this. Some more examples for discussion part. Don't hesitate anytime you ask the question so that at least concept you understand. Okay. So again, I'm going to explain from this point of view autoencoder, and then I will link to the variational.
Sir, the popular distribution used is Gaussian. Otherwise, we can use others also, correct?
Yes, yes. What happened is that if you recall, that's what happened if you are doing in image processing also. Most of the time we use Gaussian noise, am I right?
Yes, sir. Yes, sir.
So there are the regions like central limit theorem, if you are aware.
Yes, sir.
Oh, yes. So what it says that if the multiple cause for the error, so the additive effect will be always Gaussian. Am I right?
Yes. Yes, sir.
If there are multiple cause of any error, then if you sum up all the cause and error, it will be a normal. Whatever the scenario, it will be normal. Either individually, those are uniform. If you take the sum, it will behave like a normal. So most of the time we assume and play with the normal distribution. Specifically, you know that for this is this suitable, you go with that and see that what kind of learning is happening. Am I right?
Yes, sir. Thank you, sir.
Okay. So there are now going to become a lot of maths, but I will try to keep down or minimize it. But again and again, I am reminding that try to understand the concept, what is happening in that. Okay. Otherwise, inbuilt models are there and you can play. And without knowing that these things will happen. Okay. What autoencoder is doing, just quickly you just see, we have an input data and we apply this all GRELU and everything X to encode a feature. This is the encoder. And anything you either stack or deep part you are using, you can do that. This feature learning we are doing Z as a feature learning encoder. Part this Z and then we apply decoder on top of that. Z usually is smaller than X, so already I discussed about that. You can capture some greater than also. And then we use the decoder and we try to reconstruct the input data. So encoder and decoder we apply, it could be I said that it could be a convolutional neural network, it could be anything. So this is what this feature is giving X. Now in the variational and generative part, it comes out already. This loss function is this one. So again, I discussed on length. We don't use label in the case of loss function and error computing. In general, where you have studied multi-perceptron or CNN for the label data, that's another kind of problem. But the CNN can be used here also. So in this case, okay, what happened in the variational autoencoder? Just see. We assume that this Z have a probabilistic distribution. This latent variable have some distribution. Instead of saying that Z is anything, we assume that it has distribution. What I said that. And then from this distribution, this theta is a prior distribution. We are going to learn this X. Some image we want to generate. It's a generative means it is able to generate some images which even you have not seen. Okay, that part is different. So this is the latent variable you can say, and we are trying to get from this latent variable, we try to get the image. Okay. X is an image, Z is a latent vector. Okay, we want to generate. We want to estimate the true parameter of theta for this generative model. So generative model, even this is valid for the GAN if you will see carefully. So what is the parameter? Parameters means if you assume that Again, this Z is the normal distribution, so mu and theta will be your parameter. If you assume it exponential, so lambda will be your. So different kind of distribution, different kind of parameter for that. The whole idea is that what should be the mu and theta for this Z so that we are able to generate this X. How do we represent this model? How to choose this distribution? That is the simple is the Gaussian, what I told to that. And then a decoder network, how we do that? So we can, for this probabilistic function, people say that, okay, why you are worried? Put it here, some decoding function, some CNN for to decode this. We can put it and it will do that. So this PXZ, don't worry what I am saying that this probability, this PXZ you can replace with a network, nothing else. And this network will do this Z to X part. Okay. How do we train this model? Again, little bit this one. There are some MLE and other kind of approach, but okay. Theoretically, it is difficult to do that. But what happened through approximation and ANN, people have tried to get this. So don't need to go this. I will talk about that. What p theta z is? Basically your latent height variables, which is Gaussian prior, what we said. Decoder is what I said is a neural network. We can put it here. Intractable to compute. This integration is very difficult to apply. Then people say, okay, no, don't worry. No need to do that. For that also we can apply some other approximation conditions to get it. So this part just quick. So what people say that, okay, this integration of this theoretically is very difficult. So people say that, okay, for this we use some network, for this we use decoder, and then we use some encoder, and then we try to get it. What will happen? So one or two slides are little bit tricky in the sense if you are not knowing that PDF and this track to maximum likelihood, then you may not be able to understand. So, but let just sake of this, why this slide I want to show that, okay, then you can connect it. Okay, people have connected network to approximate something, some actual real which are not able to solve exactly. We are approximating through ANN and this different kind of models. What they said that, okay, why not from this X? We are modeling probabilistic network model, encoder and decoder network probabilistic. They model distributions like this. From a given X, why not we can learn some mu and sigma for the Z? Are you getting? For a Z, for hidden units, already I discussed this. And then from this Z, why not then from Z you learn again X? So this is the decoder part, what we are saying to do, and this is encoder part. From this X, produce this mean and variance of your encode in such a way so that you can get the mean and variance of encode. And from this encoding part, you use your Z, means sample from this, and again generate your output, which should be closer to your X. This is the whole idea of variational autoencoder. Actual one has been approximated. Why? Because this one is okay. The sample correction and all is going to lead toward the same solution. Okay, this part theoretical. Okay, I will. Actual closed form solution not possible, so people designed this. Sorry for that slide, but it will be a little tricky and difficult to understand. But this part you just type. What is the whole idea of variational is? For this X, get the mu Z and this using the encoder part. So you can put here the network, and then in the last two nodes of that network, you can say one node is representing the mean and another node is representing the variance. That's what you can say. And from then you collect the sample, and then from this encoding is done. Then collect the sample from this encode. Then again decode the actual X. Just see the difference from X to Z here we are getting, and here from Z to X. You generate again the image, and then again from this image collect the sample, it should be closer to X cap, maximum likelihood of original data input being deconstructed. So actually the actual mathematical model which was not able to track or able to solve exactly, people have approximated through this encoder decoder architecture such a way so that this whole phenomena can be captured using the probabilistic model. Very simple. Encoding X is giving the hidden layer sample, mean and variance. From that we are collecting the Z sample. From Z we are creating again X and Z mean such a way so that if we collect a sample from this, it is closer to X cap. This is what the idea of all variational autoencoder, and thereafter you apply the same your error function and do this analysis and you will get your result. This is what the variational autoencoder part. Leave it that derivation part, but simply that is the part of this is a generative model. It is generating this from this Z sample. Basically, just see that once the sample is generating the image, you are collecting a sample and you are generating an image. And in the GAN, remove this encoder part and it is work from the image, and then one adversarial network we train parallelly, and then we do. Okay, this is the variational autoencoder part. For every mini batch of input data, compute this forward pass and then the backward, and you can apply this. So what happened in this? If in that case, also, if you not apply the regression, it may learn, but it may randomly learn many things. But to control and to get it, what is important to learn in this specific case, we can apply the regularization. And regularization is very, very important. Already I discussed in the many domain. So what happened in the variational autoencoder generating data? Use decoder network and sample jet from the pair. Once your encoder decoder is variational autoencoder is ready, so even that you can use it to generate this image from decoding part. Almost same thing is happening in GAN. We randomly pick a noise and we generate the image, and we have another actual decoder, and then we compare it as adversarial way. Okay. So here, once we network is ready, trained, this part is used to generate the images, actual images, and this is closer to the actual one. What advantage is that this variational autoencoder kind of things is sometimes we have a data sets also, and some class of data sets are very less representative or we don't have. Okay. So for that cases where less number of data sets are there, we can play with variational autoencoder to generate the images which are closer to the actual one. See the advantage of variational autoencoder where less data sets are available scenario. That is the one reason for GAN also. Well, so you can play with that in different applications and see that, okay, once the trained, you can generate the number, data, manifold, this. You can learn with this and you will get the results. So the idea is again and again, I'm saying getting the network sample and this mu x, don't worry what I'm writing summation. All these are inside is a neural network. It could be a CNN kind of, or it could be any kind of network, but the top node is that one node is for mu and one node is for sigma. That is sure. So many application of this to generating a data where less number of data is available, you can use it and see that, okay, how it is working. Thereafter, people have gone through this autoencoder to the GAN part, people have used, but this is not the part of my slide. So you can go and see that many works on that, variational autoencoders and many huge application to anomaly detections to a different domain. People have used this variational autoencoder as a generative models. specifically the needs are where the lesser number of images are available for a particular domain. In that case, it is very, very helpful. You cannot say that we need a data set for all variety angles. So scenario where lesser number of data sets are, this variational autoencoder are very, very helpful. Again, this
Sir,
is yes, tell
sir,
me.
how many minimum number of instances training, not training here, it is unsupervised. Minimum we can have one and still it may work.
There are okay. There are one short learning algorithm. As it is, we have to find out. So there are some work on that, like one short learning algorithm, of which maybe tomorrow I will discuss, where in some cases, if even one images are there, then you can learn that. Okay. In general, if you apply any classifier and only one image, then you know that that will not learn anything.
No,
Okay.
that won't learn.
But there is a transfer learning scenario where zero sort, few sorts learning algorithms are coming up in last 2-3 years, where zero sort, even nothing is, no image is available, only some intuition or description is available in text form. Then also how we can learn, challenging problem. And another one, only one class is there, so this is known as one shot learning. Okay. But this variational autoencoder, okay, you can at least right now you just think about, okay, it's a probabilistic and it is generative, but I'm not saying you directly as it is apply for one shot. Something you have to do, to apply for one shot. That tomorrow I will discuss.
So
Okay.
minimum 20 or 30 will be enough for these things.
Directly I cannot say that, but you play and then see. Yes.
Yeah,
You need
as
to remember.
compared to classification where we really need for deep learning huge amount, but here this
No.
problem statement.
Sometimes what happens, you need to generate the multiple images and then you do the classification. So what is happening is that if I have a machine which is able to produce the images, variations of images, then okay, give me the machine. Okay. Either you need a data or a machine which can generate a data, which is similar to the data where you are going to deal. Am I right?
Yes.
So variational autoencoder, another what is the advantage is that the similar kind of images more you can generate. Getting a point?
Correct. Okay.
So this is the generative. Why generative? Because we are learning first the distribution through this part. Okay. Then collecting the sample from this, and then we are trying to make a network to generate this image.
Correct.
And it happens in the generative adverse GAN also. If you have gone through the GAN.
Yes.
So GAN, what happened? In GAN, instead of from the data generating sample, we take the random noise. Okay. We generate the image, and parallelly we have another kind of adversarial training. Okay. Where we learn actual image and then we classify and we see that this generated one is actual, closer to actual or not. And in between this bargain, we learn this network. In this case, this mean and sigma we are learning from the data. Okay.
Yes. Input data.
Input data. But in the GAN, we don't do that.
We'll continuously learn the mean and standard deviation
No.
from the intermediate generated also.
In that case of variational autoencoder, we do this.
Yes. Okay.
In GAN, I'm not touching in detail, but in GAN, this part you can look at. Okay.
Okay, sir. Thank you.
No such kind of error function then. Error function will be different in the case of generative adversarial network.
Okay, sir. I'll check. Thank you.
Okay. So this is a variational autoencoder. Can play, and there are many, some 1 or 2 quick applications are there, which I will show you before the ending. Okay. Well, the same thing, feature learning and dimensionality reduction. You can use that. A dimensionality reduction also and see that. And most of the times what happen, multiple, I think of time permits, I will show that. You can do this encoding, so you can make a network, okay? Encoder, this is inbuilt function in the keras and all you can play. 200 2000, then 500, then 250, then 10, and then from just reverse this 10, 250, 500, 200. And this network is ready and train it. Once it has been done, then the dimension will be this 10 dimensional. This in the dimensionality reduction, if you are willing to use, once this encoder, decoder, autoencoder is ready, tuned up, then what we do? We remove the encoder part and we use this one as a dimensionality reduction part. Are you getting how we are going to use? Encoder, decoder has been done. Once ready, remove this part, and this will be used as a compression technique, or wherever you want to apply. This will be the compression, image compression, if you want to do this. Because we have a decoder, it can deconstruct. Am I right?
Correct.
This
Yes,
is the
sir.
one of
Yes.
the use. This is one of the use. But there are many you go and think. So denoising and indenting is a different case. Also, something I said that some part is missing. So denoising autoencoder, I discussed that. How to fill this? This is one of the problems. So okay, I can train the model and
Sir,
I can do this.
I was thinking the previous
Yes.
slide where you were showing that dimensional reduction.
Hmm.
Just now you showed. So
Hmm.
from there, once we have dimensional reduction, after that we can go for the image segmentation also, correct?
Where
Matlab
is the
it's
image
a
segmentation?
it's a different application, but we can make use of this first half and then go ahead with image segmentation also, because there
Yes.
also we need feature
Yes, yes.
reduction.
Wherever the feature reduction, you may look at this way also. This is another way to
Yes,
look at
yes,
that. Okay,
yes.
autoencoders are also another way.
Okay,
And
thank.
another thing is that if we do with only PCA, but PCA is one this very good, but it is only the linear one. Okay, so
Yes,
if
yes,
distributions are in the non-linear space, we cannot capture
yes,
through PCA. But
yes,
here the
yes.
advantage is that using sigmoid and all, even we are doing the feature reduction,
Okay,
but it will be
okay,
non-linear. It's a manifold learning we can do through this. You cannot
okay.
achieve through that.
Thank you
Okay.
so much, sir. Thank you.
So that is very, very important in that case. Okay. So denoising, indenting, you just go and Google it, and then you will see the huge application. I cannot tell everyone. So this is very, very huge applications on that. Even for recommendation system, some what happened, it is used, people have used this. What happens, some missing data sets are there. And for that, what okay, we learn that encoding decoding pattern in this recommendation system, and we can apply this autoencoder variations also, and then we can achieve our that for those for missing part, incomplete something is not available. Okay, no problem, some data is missing, but we can do this feature extraction, and we autoencoder we can apply, we can learn those latent hidden features, and that can our job could be done. So huge application, because this recommendation system and all, anywhere, either to the any shopping mall, how to plan that, in the different location, what should be put it there, or in the Amazon to Flipkart, what should be recommended to KPSing, because if I'm buying a shoes, what next I'm going to buy. So a lot of things are there, people are using, big companies are using. So recommendation system is one of the also use of this autoencoder, which some data sets are missing, like indenting something is missing, we do. Same way, in this case, also it can be used as a recommender system applications. So derivation part, I will not go. So where you can look at to use this, some missing rating is there, like a denoise and noising part, something is there, zero is there. So again, you can construct, reconstruct, and then hidden weights you get. And then this reconstruction will be some fill weight, it will not be zero, and then job is done. So you can see that this work in autoencoders meet collaborative filtering. But this work you can see in more detail. So what I said, there's so many applications you can see that. Okay. So here, instead of going in and going, I will take some questions. I would like to stop, and tomorrow morning I will discuss on top of that how it could be used as a transfer learning and some other new domain challenging problems which I will cover tomorrow. So I will take the questions here if anybody have the questions. Tomorrow I thought to discuss, but tomorrow session I will take hands-on, and then for this, and then I will discuss transfer learning. It will be okay. And also many of the slides I have taken from Dr. Piyush Rai, one of my friend in ITK. So many of the slides, not all, I have taken. So I would like to thank them for such a beautiful slides they also created. So some slides I have taken from Dr. Pius. So here I would like to take questions if anybody have before I'm going to close this. Better to take.
Sir, some questions are in the chat box actually.
Now I'm going to see, yes. Someone is saying for, can you ask the question like?
Okay, I'll read it, sir.
No, I have
Shall
read
I
it, but yes, he can discuss now. Can we find best feature by using GA and PSO? So what kind of features and where you want to apply GA? Can you discuss?
It is better if the person can ask question. They can unmute themselves and ask the question if you are still here.
Yes, that's what I am saying. So that I can get the question directly, more detail.
Mr. Devendra, can you ask the question? Can we find best feature using GPS? What is the actual question? Please unmute yourself and ask.
Okay.
I think he's not here.
Not there.
There is another
Where you
question,
want to use GA
sir.
and PSO?
Can encoder replace? Yeah, his question is not clear. Anyways, there is another question. Can encoder replace image processing done before supplying to CNN model?
Okay, so what I said that in encoder, encoder could be also a CNN. Okay, and decoder can also be a CNN. That part tomorrow also it may be CNN there also. So where you want to replace then? So you want some feature and that those features if you want to put at input in the CNN, the same thing. Either encoding you can do that. You can do the experiment, but what you want to achieve? Because encoding
Actually,
decoding part also
we
you
can
can use as a
experiment with it.
CNN, decoding as a CNN.
Yeah.
That's what I said. You can, but encoder, decoder, this encoder may be a CNN and decoder also be a CNN. So this CNN can be used within the encoder also. If you want to do this for the CNN, you can do that. Autoencoder will give the features or some weights. That features you can pass to CNN and then build up the top of CNN and that. You can. The same way, the CNN inside autoencoder you can take also and you can play. Because to apply the autoencoder, CNN directly if you want to apply without autoencoder, so you need a kind of, you can say, label data. So you have a label data. So first using the feature only without any label, do the autoencoder, learn the features, and those features instead of actual image, if you want to pass the scene, and you can do it. This experiment you can. No issue. And then one is asking Relu or what? That question I'm not getting.
I think his question is not clear and he's not here. So,
If he is here, he may ask.
his question might be related to something you were discussing at that point of time, probably 1 o'clock. So he's not here. So no issues, sir. I think we are not getting any more questions. And
Sir, one last question,
this
sir.
way, I think we can.
Yes,
Sir?
please. Yes, please.
Sorry for having so many doubts actually. Sir, actually I understood that after encoder, once we have got the features, say feature reduction, then that can be saved, that model can be used as transfer learning for the subsequent tasks in using the CNN. That's what you were saying. Tomorrow you may discuss.
That
Same
can
thing.
be. Yes. That not as a CNN, but as a transfer learning, I will tell you tomorrow.
Yes. So we can just stop at the encoder part, save that model, and then use those weights as transfer learning, correct?
This is one way of
Yes.
utility. There are many,
Yes.
but this is not the only utility. This is one of the utility of that.
Yes, sir.
One kind of. Like
Okay.
variational autoencoder. In that case, we need the decoder part. to generate
Yes.
the images. Am I right?
Yes. Yes. Yes.
So it
Yes.
depends on where you want to apply, what are the purpose and what you are going to do. So that accordingly, in a particular application, encoding is important or decoding. So in the
Okay.
transfer learning, I will use this encoding and some applications I will discuss.
Okay, so here in the present research was ongoing research work. Usually, this encoder decoder part, we are always hearing about the GA and GAN. Otherwise, also many image processing part. Also, you have told one of the applications. So these things have become state of art, or still lot of open areas are there.
In autoencoders, tomorrow I will discuss this zero sort, few sort, and some open problems where you can look at. But still, like autoencoder was developed way back. The variational autoencoder came in 2013, and then GAN in 2014. But after that, people have done a lot of variations of that. Okay, but
Okay,
philosophy was there. And in
okay,
2013, this variational was used. But
okay.
somehow up to certain extent state of the art, but still a lot of challenges are there which needs to be handled.
Yes, it's
It's not
unsupervised. Unsupervised is still an open area, sir, correct?
in every
Unsupervised.
domain and super reason is that we have like satellite if you are working image.
Yes, yes,
So most of the data sets are unlabeled we have.
yes,
For
correct, correct.
labeled data, ImageNet and VG19 all are giving very, very good result. Am I?
Very good results, correct.
So almost not exactly, but almost things have been done. But still improvement people
Yes,
can do, but even 90-95%, 99 people are getting.
okay.
But
Thank
in the
you.
case of unlabeled data, where huge number of data sets are there, who will label them? We need
Correct,
experts to label,
correct.
and that is the real challenge. And that's how this zero sort, few sort, that transfer learning, meta learning,
Hmm,
other
hmm,
kind of variations are coming to
hmm,
deal
hmm.
with where the data sets are not labeled.
Okay. Thank you so much, sir.
So
Thank
nothing is saturated, but you can say a lot of scope in that direction is there.
Okay, sir. Thank you.
Okay.
Kindly if you mention more, uh, difference
Mr. Sudipto, your voice is not clear.
I'm not getting. Your voice is not coming.
You can write your question in the chat box for me clearly so that we can
Yes,
ask
I'm
and
here.
if we
Write it.
have. Hello. Any other question in the meantime?
Okay. So this is Manjunath.
Yes.
Yeah.
Sir, I have a question. So
Yeah.
whether the auto encoders is useful for time series applications, sir, whether can be applied and
Time
for
series.
improving the better.
In the
Yeah.
yes, in case of time series, you have to apply, like I said, that we can place CNN and other part in the encoder decoder. Okay. If you are going with the time series data, then you have to play with LSTM and other variant. Okay. Instead of CNN, you have to go with LSTM and other technique, and you can apply.
Okay.
You can, but in that case, already if you are working with the time series without autoencoder, most of the time you are playing with RNN and LSTM, these algorithms. Yes, sequential data is there. So in that case, or encoding decoding pattern is there. It's little bit change, and you can play with that with time series also.
There is another question. What is the difference between auto encoder and PCA?
PCA, I discussed that it's a special case you can treat from the autoencoder. PCA is only learn the linear kind of feature extractions we are doing that, but it's linearly it look at that it's where data sets are distributed, but that even in the terms of dimensionality reduction if you are looking at, and autoencoder advantage is even the non-linear means in the 2D plane it might be the possible that your data set is only in the circular region it is distributed, so you cannot learn those things from the PCA, but you can capture those things through autoencoder. So PCA is a linear, but autoencoder with sigmoid and that activation function, if you use, it becomes a non-linear, and it captures those manifold which you cannot capture through the linear like PCA. This is the one. Apart from that, this not only for feature extraction, for feature representation in other domain, also this autoencoder can be used in many domains. So PCA is one special case in a special category with non-linear, just linear activation means no activation is a PCA. But autoencoder have a variety of things you just change and it will act in different way. I hope you are getting my points. Ask, I think Sudipto Kumar Mondal. Yes, Sudipto.
Sudipto Mondal asked this question. Now his voice was
Yes.
not coming. So
Okay.
yeah, he got the. So I
Yeah, you
think
can, yes.
that's
Okay.
we have already taken all the questions, sir. And since there are no more questions, probably we can end the session here. I thank you very much, and thanks a lot for helping us out, distributing your knowledge, sharing your research experience with all the participants. As many participants who have joined the first leg of this FTP, there also we had the honor of listening to you. And again, we will be honored to have you here for discussing the transfer learning in tomorrow's session. And tomorrow at 9:30, we will again have Professor KP Singh with us. And for this lecture, I thank you very much, sir, on behalf of all participants and on behalf of all coordinators. Thank you so much, sir.
Thank you. Thank you, Dr. Munen, for inviting me. And it was very, sometimes what happened, if people ask the question, we feel that, okay, it is good to discuss. So I'm thankful to that. All the participants, many have interacted and asked the questions. If you ask the question,
Yeah,
then
exactly.
it will be better for us
It becomes
also
lively when people interact. Yeah.
interact. So even for tomorrow, if whatever I discuss, if you come up with the questions regarding this, you come up with that, and tomorrow I will discuss also. If you have a doubt on that way, on this topic, if you want to discuss, you have a time today. Google it, ask if you have a question, so that I'll be happy to discuss tomorrow also. So thank you all for making this more lively. It depends on you how you are going to interact. It will be also motivate us. Okay, these things I have to discuss. Thank you all for giving valuable time.
Thank you.
Okay.
Thank you so much.
Okay, guys, we will meet again at 3 o'clock when we will have Professor Shekhar Verma with us, and he'll be talking about GCNM. Okay, see you then.